Hi, I'm Stefan, the organizer and host of the emBO++, the next level conference for embedded software developers. And thanks to Leica Geosystems, you can watch this talk online for free.
I guess it's time to start. So thank you for coming to my talk about Json parsing called Eventful Parsing in Parallel Bytes. I'm a software developer at Siemens Technology right now. Before that, I was working at Ubuntu Touch or Canonical to work on freeing Android devices from Android. And I still do that to some degree by helping out the Reports Foundation. And before even that, I was working at Electrobit, writing automotive software for infotainment systems. So yeah, today I'm going to talk about a JSON parsing library. I don't want to pitch it as the perfect end of all JSON parsing library. It's more a talk about the design decisions and compromises and problems that I encounter and why I came up with what I had. And yeah, so I'm going to explore a bit of that and show you why we did that. And so we did that because of our product. At Siemens T, we built a C++ framework for embedded devices in the area of Cortex M4, ESP32. Those devices are connected to the internet, to a Amazon service for managing those devices. You can see a screenshot of that system on the right. It allows us to monitor the MCOs, send config changes, see what's going on, and aggregate data if we need to, or update firmware, change the configuration, or see measurements that the sensors did on the devices. And to describe the behavior on the devices, we use a data flow graph, and we have an editor for that. Out of that editor, we get a JSON document that tells us what sensors to connect to what actuators, what values to extract, and how to compute them. So the device takes that information, parses it, and operates that one. So as with most things in software, we add features, and then we hit RAM or ROM boundaries, and then we need to shrink again. So we remove stuff or change stuff. And one of the things that came in handy, and I would like to give a shout out right here, is BoostDI. So instead of using a factory-like construct, we use the dependency injection container by BoostDI, which helped us a lot to make things small. So I was at the last emBO in 2019. So not the last one. My last one was in 2019. And when I returned from that one, the next growth pain that we had was regards to RAM usage in this bespoke JSON document. And so we need to solve it somehow. But before I jump into that, I would like to show you a ancient Greek clock, which was found at the coast of Greece, and it is a mechanical computer that predicts astronomical positions centuries in advance. And that knowledge on how to build that thing was lost after the civilization collapsed, and it took us more than a century to get back to that level. So I think, yes, to some degree, you shouldn't build a parser if you need one. You should pick one that fits your needs. And if something is missing, just add it. But we should be able to, know our infrastructure, know how it's built, and be able to reproduce it whenever we need to. So, and besides that, parsing is a standard computer science topic that is interesting to explore. So I feel rather lucky that this was something that I could do as part of my work. So back in 2019, there were lots of JSON libraries already available. I listed one of the nicest ones here. Niels Lohmann's JSON library is probably one that has the nicest interface. And there's RapidJSON, which is pretty fast or known to be fast. Then I only added JSON 11 because it comes up in a lot of searches. And this list is by no means complete. There are just too many out there. SimJSON is one that is particularly interesting because it's very fast. I guess right now it's the fastest ones because it's the only one out there that uses SIMD operations to look at multiple characters at once. And I think I didn't have that on the radar back then. Same applies for BoostJSON. I printed that in italics because it's an outlier in this list, but I only realized it when preparing this talk. But it didn't exist back then, so no option for me. I only mentioned C++ libraries. There's also lots of C libraries out there that we could easily integrate. One special case was Jasmine, which I looked at. It is basically just a tokenizer. And by that, it's very fast. And it kind of claims that you can do incremental parsing, but I couldn't figure out a way that you could give it only a part of the document, operate on it, and then continue once you have the rest of the document or later part of the document. So I ruled that one out also. I said incremental parsing because, that's the issue that we have. When we want to parse JSON, it means that, we either have the JSON document mapped to our memory and we don't have to spend memory on the document itself, or we have to copy it into memory from the network or from an external flash chip. Then we can start parsing. And then depending on how the library works or how it's configured and the memory the JSON document is in, it can allocate inside the document itself, or it needs to start allocate even more. And only then we can start extracting the information that we need. So from every perspective, it's not really what we usually have to do with JSON documents. So what we rather would like to do is get a fixed buffer of our JSON document that fits in our memory and just start parsing. And with the first byte already start extracting what we want from our JSON document and continue on until the document is done, or we hit an error and we stop parsing. So usually if I want to solve something that's related to parsing, I turn to stuff like Boost Spirit, but also there's a recursive Descendant parser, and for that one, you need coroutines to jump out of any nested position in your document. So that was also not an option. So my first step was looking at Niels Normann's library and extending and adding a new code parse to consume characters as they come and handle input as needed, and keep track of where I am in the document and keep track of what to expect next. So I was manually writing a state machine and unrolling it in switch case statements or in loops that turn out to be more complex than I wanted them to do. And being on a job assignment and doing it in a somehow time box way, that's nothing that I wanted to do. So I soon realized I need to do it maybe with a state machine library. And before we jump at that, one question that often comes up is, when do you start using a state machine library to represent a state machine? Because most of the time people just throw a bunch of switch case statements somewhere and be done with it, and then pay the price of maintenance. So in this case, it's clearly to see because you have two pieces of information. You have your current state, where you are in your document, and you have data that comes in. Then you need kind of do some form of double dispatching on what to do next. And then when you move from one state to another state, you have certain actions that you have to execute. So that clearly leads to a state machine. So once you have this kind of double dispatch or quadratic complexity of code that grows as you add features, add states, add types of inputs to your enumerations. So when you go for a state machine, you have various options too. You can use a basic finite state machine, which gives you states, conditions, and actions to communicate what you want your state machine to do. And yeah, if you this is usually also the target for regular expression libraries. If you describe your problem as a regular expression, it will convert it in one of those finite state machines. Yeah, but there's also hierarchical state machines. They give you more options to declare what you want to do, because you can group states together, so you can reuse transitions, and so it's a better way to communicate, or it's a more elaborate way to communicate what you want your system to do. And yeah, so I would like to give another example, because I was working in the automotive area before. This one is EB Guide Studio, which is a software to describe infotainment systems based around the idea that the system is controlled by a hierarchical state machine. And what you can see here is that the leaf states also have widget trees attached. So you not only have actions and conditions and state names to communicate what you want to tell your coworkers and whoever looks at your system, what the system should do. You can also attach more. So you have implicit behavior that is attached to your state, which is also something pretty nice to do. And it doesn't have to be widget trees. I mean, whatever your problem domain is, you could change or build your library in a way that the state in itself has an implicit behavior. So that led me, since I'm biased to that, because I was working on this project while I was at Electrobit. I was biased towards hierarchical state machines, and Chris Jacek again has a nice library called BoostSML, which has a very simple embedded DSL front end and has very efficient backend. So if you look at this GitHub page, he has lots of examples on how small the resulting state machine binaries will be. So there's nothing to complain about, only that I was missing some specific features in the way you describe the state machine. I always wanted to share transitions, and so not only group by semantics, but also group states by shared transitions. So that's something that's not directly possible, or I couldn't find a way back then. So I thought, let's make a small change to the front end and potentially adapt the backend so that I can jump from one compound state to another compound state, and inside the compound state to a leaf state, and inherit all the transitions that would be available then. So I got caught in a trap of working on state machines again. So this here is one of the central pieces of the backend code of BoostSML. I wanted to show that because it directly creates the switch case statements for the states in one compound state. And I tripped over this code here when I tried to adapt the backend. 2 years ago, and it is 2 years ago. So I don't know exactly what made me fail in adapting the backend, but it led me to rewrite the backend entirely with kvasir MPL, which led to a state machine library in the end. So yeah, so in the end, I changed the front end a little bit. I allowed to declare states with compound states with its leaf states in a single expression, and also jump from arbitrary states. So you're not limited to jump from a to one state to a compound state, but you can jump through compound states into a leaf state. So I would like to show you now the result of that in the Json Parser. Can you see the yeah? So the Json Parser state machine is around 130 lines of transition code. So the difference in the front end is you don't have to say state plus event equals a new destination state, because you group the compound states together. So the event is now the first element in the declaration, and then you make equals to either internal, which says it's an internal transition, or the destination state. And yeah, the call operator to declare a compound state. So as you can see, there is stuff like end of input, EOI, scattered across the state machine, because I need to handle the fact that the buffer that I'm processing is at its end, and I then need to either trigger a callback or event that this is the stuff that I parsed so far, or not. If I'm parsing a number, end of input doesn't mean anything, because I'm storing the number inside the parser. A number is not a problem to store. It's just yeah, whatever you specified in your traits, single value. And yeah, we can go a little further. So let's see. Once I hit a brace open event, I need to remember that I'm entering an object. Then I jump into the member state, which is down here. And once I'm in the member state, I'm expecting quotes. And once I get into a quote, I can start parse a name, and I will accumulate a string view here. And once I hit end of input, I can tell whoever called the parser that I'm done with that part of the name. You need to store it because the buffer will be gone soon. And it continues, and later we'll it will continue a process on that name, but it will never have the whole token in memory. The same goes for strings. We can have strings that are arbitrarily large, and they can be bigger than the input buffer that we are processing. So let's go back. So I would like to talk about the state machine algorithm that I'm using. So whenever there's an event, I need to figure out where I am in the state machine and what transition to take. So I'll just compare the transitions attached to a state with the event, see if it has a condition, and otherwise go to the parent state. Once I found the transition, it depends on whether it's an internal transition. Then I would just execute the potential action. Otherwise, there's more to do, because I need to exit and enter states. So since you need to exit and enter all the states that are between the source and the destination state, you need to figure out whether the destination is part of the same compound state, or a child state of that state, or a parent state. So one way to do that is by having a nested sets model. So each of your state IDs is assigned in a way that the child state comes after a parent state, and each compound state knows the number of its children. So figuring out if a state is part of the set of children of another state is just a range check. So you end up just doing a bunch of range checks. You exit the states that have an action for exit. Then you execute the attached action if there's one. And you do the same for the enter actions, just in reverse, which is also something that you don't have to do when you know that your state machine has no enter or exit actions. So you can basically just at compile time leave those parts out. And yeah, once that's done, you have your new current state. And then potentially if the new state is a compound state that has an initial transition that you have to follow once you enter the state, the loop continues on. So here's a small extended patch toy example. So once you get the wake up event, you enter dog mode, you start searching directly because you have this initial transition attached to your start state. And if the doorbell rings, the reset timer action will be invoked. And since you are in searching state, the transition, the state search will figure out that it has to leave dog mode, but it has to enter barking mode right away. So then the only option is that someone uses a laser pointer to get you into cat mode. So yeah, that's basically it about the state machine algorithm and yeah, how to read those state charts. I would like to give more details about the backend because that's the thing that I changed. So instead of using just switch case statements or tables for compound states, I've put all of the states in a single table, and I use kvasir MBL to traverse the whole expression tree, figure out how many states I will need, figure out how many transitions I will need, see how many actions and conditions I will need, and then pick the most fitting primitive type for those elements, and then construct a templated structure for states and transitions to hold that information. And those are directly initialized. There's no init code for that. For conditions and actions, I'm always struggling with the problem that I need to store a lambda directly in an array. And there are some hacks that work on different GCC and Clang versions. But depending on your GCC and Clang version, you have some init code to initialize those two arrays. I'm also not allowing that those actions and conditions have bindings, because then I cannot store them in a plain array. So they need to be bindingless and mappable to a function pointer in the end. So otherwise, it will not work. If I wouldn't do that, I would need a structure like std function to store the actions and conditions in, and that will we tried it. That increases the ROM a lot. So we settled with plain function pointers for that one. And we pass in a user-defined context object, which is also type safe and fine. And whatever you need as a local context can be available at the point of declaration of your lambda 2. So there's actually no other limitation. So the signature of conditions and actions is predefined with.
Wir sind hier in einem kleineren Grossraumbüro.
Bei den Leitern habe ich die Freiheit, dass ich, wenn ich anfange und wenn ich höre mit dem Arbeiten, eigentlich selber einteilen kann.
Overall, how I will do it, it's just up to me and they give me a lot of freedom.
Für mich ist die Faszination, mit anderen Leuten einen kreativen Moment zu generieren.
Great colleagues, great environment basically.
it's really nice here and I don't have any issues living here.
Am meisten schätze ich in den Like Geosystems, dass wir ein sehr junges Team sind, sowie dass ich auch meine Arbeitszeit in einem gewissen Raum selber bestimmen kann.
And I could merge my life hobby with my office job.
Das Besondere an der Leica Geosystem ist sicher die Kultur und die Dynamik, die es gibt in dem Team. Es ist jeden Tag ein bisschen anders.
We have good organization which will help you to get used to the company in the first couple of months especially.
Das ist sehr interessant und ja, macht mir Spaß.
Your context type. So in the end, that turned out that our Json parser is about 5 kilobytes big in ROM. And yeah, state table 280 bytes, transition table 510 bytes. The algorithm code and parser code, so all of those actions that are attached, and it varies depending on your target, it varies depending on your compiler settings. Those things vary a bit, but it stays in that area. So yeah, it is definitely an improvement over what we had before in terms of ROM size, and also definitely in terms of RAM size. As I mentioned, I'm only emitting events. So when you hit something in your JSON document, like open curly braces, closing curly braces, you get a callback or an event for the beginning or the end of the object. Same goes for arrays. For values, like numbers, the parser stores a local value that is used to accumulate whatever you find in your document, and it will pass on the value. So you only get an event once the number is done parsing. You don't get an event for each character, of course. For strings that can occur in names of objects or in string values, you get multiple events. You basically get a name start and then a name end event if the whole name is inside your document, inside your buffer. So if everything fits inside your buffer, you only see those two events. The first one contains the whole string view. But if you happen to have only, if you happen to have the name or string and a boundary of your input buffer, you might end up having only a part of your name inside your event, and the rest will come with the next buffer. And the parser basically assumes that you will throw away the buffer that you used for parsing so far. So it will, in this case, emit that event. So if you want to keep track of elements of your document, you need to keep track of those events too. So and this can be annoying to write, annoying to keep track of. So we came up with a set of event filters that would process those events and store only the necessary information. This is an example from our source code that parses the connectivity information from our node graph. So the way you have to read this is from bottom left to top right. So the first JSON object is device. Then in that there's a connections object, which is tracked by this parse node. And then everything inside this device connections object will be forwarded into the first parameter of the parse node, and all spreads the events out to all of those event handlers or event filters. And there we will handle an array of objects that have a dest element and a source element. So the from the dest element we just take the number, and same for source. And then there's another object in that object that has a port as a name as a named object. And there we have source and destination ports. And yeah, all of that gets accumulated in local arrays. And once we have done processing one array element, inside connections, we will call a function. So that's the purpose of this event handler. It keeps track of the fact that you have you've completed one element in an array. So how did we write those state machines again? So the parse state machine is a bit more complex. It consumes the sequence of strings here. We also have like arbitrary elements. So if you don't care exactly about the parse, only some of those steps are necessary to get to your data. You can also have an arbitrary node inside here. And it doesn't fit on a slide. So I picked the on-array element one. And yeah, it basically keeps track of all the values that are inside an array element, all the values because, all of the objects and nested nodes that can be inside an element. So you can have an array with additional objects inside, and the objects inside could have arrays again. So it needs a counter. So the runtime cost of that element is just the event parsing, event handling, and the counter that tells you how deep nested I am in my array element. So whenever we hit, when we go back to level 0 and we complete one value, we basically trigger the attached action that is attached to the on-array element that you've seen earlier. So yeah, what did this do to our project? We are using far less RAM. We are not afraid of consuming big pieces of JSON documents. The ROM got smaller. I cannot tell you the exact number because the event filters also contributed to our ROM usage, and we had different versions of that implemented. Some used the function underneath, others, and then later we removed them again, so we got smaller again. But all in all, we use less ROM for our JSON handling code, and that code turned from basic imperative, go through nodes, check if node is whatever I want to have, and yeah, to a very declarative and very condensed pieces of code that are easier to look at. And that's basically it, but not yet, because while I was preparing this talk and I had to remember stuff that I did 2 years ago, I actually wanted to present that at the end of, in the last emBO, because it was basically done at in the fall of 2019. And so I now had to look back at what I did, and I also looked at the alternatives. And back in when I open sourced the library in October 2019, there was no alternative yet, but things have changed since then, because Boost JSON was released. I don't know when exactly, but I dated back the GitHub repository to November 2019 or so, and where the project was started. It is what I didn't try to do. It is an unrolled switch case parser that does everything with switch case and goto, of course. And it has all of those end of input checks scattered everywhere. But yeah, I would like to add that this is not what they advertise, because the fact that this parser also offers this is also hidden, because, I mean, no, not hidden, but the basic frontend is a DOM parser. You get a DOM out of it. You can do partial incremental parsing, but the basic idea is that you get a DOM out of the parser. But you also have access to the parser underneath, the parser core, called basic parser, and you can attach your own callback handler and not use the one that will create a DOM, and then do incremental parsing too. And as it turns out, after measuring performance and stuff, it's more than 10 times faster than what I came up with, but also 7 times bigger in ROM impact. If you manage to leave out everything related to writing JSON again. So if you only take the basic parser that in all the callback function, and you also have to, but then you also have to write your own event filters. So if today you need this type of JSON parsing, you don't want to store the document at once in your memory. Like, for example, if you're streaming on a network and you have a specific network buffer and you just want to parse what's in there, and you don't care about the ROM size, and if you build your own event handlers or use the ones I have on my GitHub, then it's probably the best library to use, because you get a lot faster parsing. And yeah, that's basically it. The library is on my GitHub. HSM is the state machine library. Async JSON is the JSON parser, and of course I was using kvasir MPL. So this was 2 years ago. I'm not. So in the meantime, we did other stuff, and we are in the process of moving away from those JSON documents, moving towards binary as protocol, and also the node graph that you saw earlier. I'm right now working on a kvasir MPL library to basically calculate the topologic sort of the graph at compile time, and also integrating that in our build so that instead of sending a JSON document, we send a whole framework containing all the node types that we need, and assembled in a way that it's that we can leave out all those node types that we don't use, and also leave out the JSON parsing for that. So JSON parsing is not like on our agenda that much anymore, but I still want to rework the state machine library. I want to either get it back into SML or get it to a faster state. When I made the measurements for Boost JSON, I found 2 or 3 things that I could do to easily get out 10%, 20% faster parsing for the library just by changing HSM. So that's basically it. Time for questions. Okay. Boost Spirit, those compilation times, yes. Boost Spirit, I made a bunch of coworkers very unhappy when I used Boost Spirit. I was told it got better by then, but yeah, that's something problematic. Yes, so this is open source. You have those links. Paul asks, did you contact Chris about the work? I have a bug ticket open at his library about improved hierarchical state machine support. And I also have, yeah, that's usually how the conversation goes. I open a bug ticket and then I'm supposed to fix it. I hope that I get to that. I don't want to bug him. He has contributed so many nice libraries, and I don't want him to focus on something only I and a bunch of others need. So yeah, I'll try to get this one in, or as an option in without breaking the existing backends. Yeah, and also Odin, if you take a look at the HSM kvasir MPL code, this was one of the cases where I end up writing my own flatten meta functions, and I'm not happy how the code looks of the compile time transformation, because I always end up doing a fold right or fold left on all of my input, and I would like to get a better idea how to do it in a different way. So yeah, maybe if someone looks at the code and makes a proposal, it would be nice. CBOR or BJSON. Binary JSON. How easy would it be to expand HSM? You probably mean async JSON to support CBOR or BJSON. I don't know. I think it would be another state machine because you probably have different events that you have to handle. So I have to look at that. We want to jump to a binary JSON format for our stuff, or a binary format that represents what we have as JSON. So yeah, once we get to that, I will have a look at the libraries out there, if there are libraries that allow us to do incremental parsing of our configurations, because we don't want to go back to where we need a big chunk of memory for whatever we get. So that's about it. If there are further questions, I'll stick around.
If you found this video informative, make sure to subscribe our channel. Click the thumbs up if you liked it, or leave us a comment on what we could improve. If you are looking for a job in the embedded industry, or you've got one to offer, drop us a mail to jobs@embo.io. That's jobs@embo.io. And we'll make sure that you match up. My name is Stefan Bückelmann, and as long as you keep watching, we'll keep covering the internals of the embedded industry.